guys that are going to recording. Well, participant 1 communicating with participant 2. They're both participants. We're talking about communication diagrams and how they represent the same thing as sequence diagrams, but in a different way. This link here, that's the solid line in between them, is called a link. And that link tells us that these two participants are going to interact with each other. It tells us that these two participants, can you still see the screen, guys? Okay,
no.
I don't understand this. Okay, this is making up words. Right, let's try this one more time. Can you see it now?
Yes.
Okay, I'm so sorry about that. Right, so that solid line is the link, and it tells us that these classes, these participants can interact with each other. Message A and message B are communications from participant 1 to participant 2. The numbering on them tell you the order. In a sequence diagram, what told us the order? We didn't need the number, even though some tools do it. The fact that the messages are going from top to bottom, that's what tells us which one is first, which one is second, which one is third. That's the difference. So a message communication diagram is shown using a filled arrow from the message sender to the message receiver. We just saw that. Similar messages on a sequence diagram, a message's signature is made up of, similar to messages on a sequence diagram. Message's signature is made up of, again, the message name, list of parameters. We also need to show the order in which the messages are invoked during the interactions, and we saw that we were able to do that using the numbering. Now, how do we show nested messages? In sequence diagrams, you could tell that we're looking at a nested message because a message went from one participant's lifeline to the lifeline of another participant, and before there was a return, or before the particular activity in the original sender's thing was over, we saw another transmission. So you could tell that the message was nested, just by how it was laid out on the diagram, right? Okay, how do we show it in a sequence diagram? Well, if you look at this diagram, we are seeing a message A being sent from participant 1 to participant 2. And then we're seeing 1.1. So the first message is labeled 1. If you see a 1.1, it means that it's a part of, it means that that message is being sent as a part of completing the original request, the one that was labeled number 1. Does that make sense, guys? Make sense? Make sense? Likewise, if you look at 1.2, it means that there's a second message that's sent in relation to the original message A. So in other words, participant 2 has to evoke message C and message D in participant 3. So we have to realize message C and D are in participant 3. But participant 2 is dependent on the invocation of those two messages in order to complete message A. Make sense? So they're like two function calls inside of the definition of message A. That makes sense, right? Yeah. If it means that? Yes. There's a, no, the fact that there's a call is not what tells you it's an aggregation relationship. Really. What will tell you that, because the call can be based on a dependency as well. What will tell you that it's an aggregation relationship is the link. You can't tell when you look at the sequence diagram. I don't know if you can tell in a sequence diagram. All right, how you know that it's a dependency from a sequence diagram is if there's a dropped message. Or if you can see where something was created later. Those tend to be dependencies. The best way to tell whether you're looking at an aggregation or a composition is really the class diagram. The sequence diagram you can't really tell. The sequence diagram you can't really tell because the sequence diagram doesn't tell you the makeup of any of the participants. It just tells you that the participant has access to a particular function in an object. But you could have gotten that object via parameter. You see what I mean? So for example, if you get, it could be that participant 2 got access to a participant 3 as an argument in one of its operations. No, it wouldn't be an aggregation. That would be a dependency. It's an aggregation when you see it as an attribute. Like in Java where it's private something, or in the beginning you have a reference being created. That would be either an aggregation or a composition. But once it's an attribute, that's what we're talking about, aggregation or composition or association. But it's a dependency when the argument in one of the methods has it can only be called, that operation will only work if it gets a parameter that is of the type of the object. Then you set that's a dependency. Making sense? And then you'll notice that here, message B, it doesn't have, this one is not nested because you don't see any 2 points, anything. Would you say this is easier to recognize a nested message than the sequence diagrams? It's kind of more obvious on a sequence diagram, right? Okay. So here's a comparison with the sequence diagram. With the sequence diagram, we don't have to label it 1.1, 1.2. We don't have to label it any at all. Even if you didn't see this message here, even if you didn't see this number here and this number here, it will be obvious based on the fact that this message is up here and this one is down here. That message 1 was first, and that message 2 is being called to satisfy something inside of message 1. Can you see that? So you can see it's nested because these 2 are inside of the operation of message 1. It happens during the time that message 1. So this box is representing the full execution of message 1. You can see that these 2 messages are being passed during that time period. When messages are sent in parallel, sequence diagrams need complicated constructs such as part fragments, show parallel segments, or parallel messages, loop to show looping, and so on and so forth, right? Communication diagrams use their number-based message ordering by introducing a number and letter notation to indicate that a message happens at the same time as another message. I think this is more complicated. We're using a letter and number combination now. So, the 2A, 2B, and 2C are invoked at the same time. That is, they're invoked concurrently because they have the same number sequence on them. So that's all you tell. Remember, these lines wouldn't be there. These lines don't have anything to do. That's just the notes.
So what is the trigger of the 2A?
Okay. The returns, you're gonna see them numbered as well. So if some, but you're not gonna show, it doesn't always show, just like in the sequence diagram, it doesn't show a return unless the return itself has some data on it or something that you need to show. You don't usually show it. But you'll see in a bigger example a little later, you'll see examples of messages going in the opposite direction. The trigger for any communication diagram or sequence diagram is a trigger for the use case. Yeah, whatever it is that would initiate that use case is what would start that scenario. How do we show looping? Well, you put the message that you want to happen repeatedly, and then you put an asterisk, and then you specify the constraints for the loop, the conditionality for the loop. You can also send a message based on a condition. So you can say that this particular message will only be sent if something is true. And that's like the else option in the out or the option message frame in a sequence diagram. Out or option segment. So fragment from sequence diagrams. In sequence diagrams, we saw how participants sent messages to themselves. We would see the lifeline, activation bar, and then you could see the message being transmitted to another activation bar, indicating that there was another message that was being invoked on the same participant. In a sequence diagram, you can see this line here represents a message to itself, and here's the message. They look similar. So let's just look at these two diagrams. You're familiar with this one. This is what we did last week in lecture. I'll just make it a little bigger. Everybody remembers this? So I had the actor was sending create new blog account message to the user interface, and then select blog account type. And remember that we're actually at the end of this activation bar. We can imagine the return messages here. Yeah. Then we see the actor enter author details, which results in the creation of the author details object. Then the actor clicks submit, which takes all of this time in order for everything to be complete. And submitting causes the user interface to send this message to the create new account controller. Create new account controller does its process here, which invokes several other messages. So for instance, it sends a check author details message to the author credentials database. Then in the opt segment, we see what happens only if checked equals true. And so we see create author details. We see the create message or creating. So this is associated with this line here. That create message is saying create the new blog account object with these author details inside of it, and so on. We did all of this last week, and then once that is finished, then we know that the create new author details controller sends a message, tries to send an email, which then invokes the email system. All of this is happening only if check equals true. And then after that, we see a destroy message that destroys the author details because we don't need it anymore. And that will happen whether or not check was equal to true. And then we have a return message going back to the UI, and then the notification goes back to the actor. And these two messages are asynchronous, right? Good. Now let's look at. Go again. It's just destroy because in some languages, what you want to indicate to the developer is that this particular object is no longer necessary, and so you can use a destructor to destroy it. This is not relevant in a language like Java because once the object goes out of scope, it's understood that it can't access again. So the system automatically garbage collects the object. It was just used to create, or it was created up here. It was used so that we could use it in the constructor for the new blog account. It needed an author details object. Well, you could have done that as we explained last week. You could have just taken the, you could have just said, because over there we have enter author details at the beginning. At the beginning of the activity, this third message here, enter author details. You could have just taken name, email address, password, blah, 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 and pass them one at a time as different arguments in the constructor. But the constructor is designed, you have to work with the interface that you have. So the constructor says it needs an author details object. Then somewhere you need to create that author details object and pass it to the constructor for the new object, new blog account objects to be created. Yes, Shannon. What do I mean when? Are deprecated? Oh, it just means that they're not supported. It means that they're not supported. So it usually comes up as a warning. It's not usually an error, right? You can use it, but it's not supported, and sometimes they don't behave in a stable way. Yeah. But they usually just say that method is deprecated, and there's usually a method that replaces it. So like the sometimes it's not only method, sometimes it's the class. So like for example, you'll have the date class. Long time ago you had something called a date class, and it worked a particular way, and then it was replaced by something called time date or date time or something like that. So they said the date class is deprecated, and it's not that it would not work, but they don't give any guarantees about how it would work. That's what it means. Okay, so right, so now we're going to look at communication diagram. And the hint is that this communication diagram is doing the same thing as the sequence diagram. So first I'm going to make it back to its original size so you can look at, I need this thing to roll. Why does this go down? Don't worry. You can't see everything, can you? Why are you seeing this screen? No, no, what you see, I want you to see. Anyway, what am I doing wrong? Why are you seeing this one? Oh, okay. Anyway. All right, so back to what we're focusing on. Do you like the communication diagram? Can you see it? If you were to choose between the communication diagram and the sequence diagram, which one would you choose? All right, let's look at the communication diagram, and then I'll ask you again. So I'm going to blow it up. I hope that you can see. Okay, so just look at it for 2 minutes. See if you can follow the messages, and then let's talk about it. All right, so you should be able to see the first 3 messages that go from admin to administrator, right? So you have create new blog account, select blog account type, enter blog author details. That's pretty obvious that this is first, this is second, this is third, but the numbering is there. If the number wasn't there, you would have a clue what to think, right? The number is there. And then what happens after the third one? Enter this. Going to work with 3.1 next, right? So the next thing that happens is that we'll have this create message, and that's where the author details object is created. But it's not as obvious that author details object wasn't there before. Whereas with sequence diagram, it was obvious when it got created. But we know it's created because of this create message. And then So I have to come back over here and we'll find out that the actor clicks submit.
And then that triggers create new.
And then we need to find program, but there's a 4.2 here. Where's that? Oh, here it is. All the way down here. The nowhere over here. And then we need to come back up here.
No, it goes to the right. It's
Oh yes, sorry. I'm sorry, we're not here yet. We're actually at 4.1. Where's that again? Right, so we'll check the author credentials. Okay, you get the point, right? Okay, you need to follow the numbers and you can't just look at the arrows, you have to follow the numbers, and if you can't find. Now, if perchance you had thought that after 4.1 or after 4 was 5, then you would have forgotten some of them. But then let's say you realize that there was a 4.1. You might look for 4.2 next, which will be up here, which is what I did. They have to really look all over the diagram and keep checking to make sure that you're finding what is the next thing. But one thing that it makes very, very clear to you, which the sequence diagram does not make clear, is which objects will interact with which objects at some point in time during the interaction. It's very obvious when you look at it, for example, that the account creation user interface will connect at some point, interact with the actor as well as the account controller and the author details objects, right? Whereas when you look at the sequence diagram, you'd have to kind of follow the arrows to figure that out. You wouldn't really realize necessarily exactly who the UI was interacting with, but it tends to be the elements. In a sequence diagram, you tend to line things up according to the order that the first being communicating in. And so you tend to have in a sequence diagram, after the actor, so you'd have an actor, but after the actor, you tend to have a user interface, then a controller, and then, well, this has more actors, but down here, if you look, you'll see an entity class. So you tend to have, remember I showed you that pattern? You tend to have UI, controller, entity. And the controller is in between the UI and the entity classes. And there are multiple entity classes. Sometimes they talk directly to each other, but sometimes it's the controller that talks to all of them and then works out something and gives it back to the UI. And then sometimes you have another boundary class on the other end, and that boundary class can be something that handles persistence. Sometimes it's like a database manager. So for example, the author credentials database is a boundary class. And then a boundary class. So that is it for communication diagrams. I just wanted you to see, to just get a sense of what they're like. So I just have some, and I hope you guys are going through the slides and watching the videos. Yeah. Do you know that I discovered last night that not one person looked at the video for lecture 7B or 6B? Not one?
I discovered that.
Huh? That's true. But I thought that since you had exam, you'd been, because somebody emailed me and asked me for it. But I looked at some of the old videos too, and I realized that with all my effort, you know how hard it is to do this? Upload it and sit and wait for it to upload it.
So you discovered.
Because tell you how many views.
No, but suppose it's I don't know the extent. That's what I did.
Oh, okay. All right. I get catch. Okay, all right, so let us go to state diagrams. State models are used to help us to talk about, oh, I had this, oh, I remember why I mentioned videos on the lecture slides. When you're going through the lecture slides, many times you don't get to go to the last 2 or 3 slides, and they tend to have questions at the end or things for you to consider. So do that. Look at the last ones. They usually have summary things or comparisons and so on. So you can look at this and no, I should not have done that. I need to come out of this one. Yes. Soon, but I don't want to fall too far behind. All right, so what do we use state diagrams for? Show the state of objects in a system. What else? So it shows states. What else does it show other than states? No. Sometimes it shows some behaviors. What else? It can show behaviors within states. It talks about the transitions from one state to the next. How many states there are, what those states are there any special behaviors exhibited by an object or a participant or even a system during a particular state, what triggers, what kinds of events could occur, and what transitions can take place as a result of those events, and are there any special behaviors that occur during the events, right? Why do we want to do this? Because our systems have some objects inside of them whose behaviors are determined by their states. Sometimes you have an object and the object behaves in one particular way, especially when you're doing coding for like embedded systems or games or even some banking systems. You might even see it for trading systems, trading platforms, stock trading platforms, and so if particular states exist, then this particular thing should happen and so on. You don't use state diagrams for every single type of system. In some systems and some objects, there isn't anything significant about the state of the object that invokes behavior, particular behavior. So, for example, if you have a student class, and what a student class do is that student class will just register and then they update the database. Database updates that the students register for these courses, and the student don't really do anything else. You know, it's really just a matter of persisting an object. And you don't use a statement for that. But in that same system, you might have something else. You might have another object, like, for example, a timetable. And maybe the timetable is randomly generated at a certain time of the semester. So, well, no, that's not exactly the next. But yeah, you have to look for the objects that have time, states change related behaviors. So if you look at our nursery manager, the nursery manager, we saw that the child could actually have multiple states. Remember, we said something like the child could be registered, unregistered, deregistered, and I think that could be, yeah, I think those are 3 states. I don't know if there's anything else. If we look back at our patient or clinic system, we saw that patient record could be open, closed, pending, open, closed, pending, and there was something else as well. Everybody remembers that? And when it's open, only certain types of operations can happen. When it's closed, only certain things can happen, and so on and so forth. So that's a good way to manage the behaviors that your system will demonstrate. And there are patterns that go along with these types of systems. Systems where the behaviors change based on states. So everybody remembers we had a state pattern in our list of design patterns. So you can actually say, well, instead of going on writing, if state equals this, then do this. Else, if state equals that, then do that. Else, if you can a way to represent state as an object, state as a class, and subclass that state into different kinds of states, provided behaviors that relate to state and use abbreviations to include the state into your object, then it means that as long as the state of the object is changing, then the behaviors that are related will be different. But we'll come back to that. When we're doing tutorial next week, you'll see. We're going to see now. The state of the object is usually just related to like it can be one attribute inside of the class that defines the state, or it can be a combination. So, for example, with the patient management system, we saw that or the clinic, we saw that when the patient just comes in and they register, their record is now considered open. But after they see the doctor can close their record. I think close was the term we used. If the doctor sends them to do a test, the doctor doesn't close their record, rather they automatically end up in a pending state. If they're in the pending state, it means that test results can come in. It can be. An object can be more than one state at the same time, which you'll see in a while.
We create more than one state objects, we have like more than one state.
State machine diagrams help us to model states of an object and events causing state changes. The account application object could have the states pending, accepted, and rejected as possible values of an attribute, say abstract, and change states upon events such as approve or reject. So these are examples of events that cause these state changes to occur. A state machine diagram allows you to model this behavior. So as I said before, they're usually used for only certain types of systems. And it's not only, so it might appear that we're only talking about machines. And I'll put in a slide to talk about that later. There's actually a slide later on. It's not just talking about machines like, when you look at textbooks, they tend to use machines like clocks, alarm clocks, coffee makers, microwaves, elevators, and sometimes you see games, yes, answering machine and so on. But it can also be applicable even in business applications. So here's an example, another one of our typical examples of a light switch. So on and off represent the two possible states of the light switch, and the transitions that can exist between them are lift switch and lower switch. And those two events can cause transitions. The lift switch is an event or a trigger. Did I say something else? I said transition? No, okay. And lower switch. Lower switch can only occur if you are in with state. It can only happen if you're in on state. And lift switch can only happen if you're in the off state. So a state diagram consists of states drawn as rounded rectangles and transitions. And transitions drawn as arrows connecting the states. A transition represents a change of state, or how to get from one state to the next. A state is active when entered through a transition, and it becomes inactive when exited through a transition. So let's look quickly at this one. This is the same account application object. Now you have to realize that state machines can be applied. You usually have a state machine being applied to one entity. Either that one entity can be a whole system. So if you have a state associated with the whole system, like for example, an elevator. An elevator is an entire system made up of many subsystems. But whether it's moving up or it's moving down, that represents a separate state machine. Now there might be other state machines inside of the elevator, like for example, which lights are on, whether lights are off, the alarm system, the cooling system that's there, and so on. You could represent any of these with state diagrams as well. But the point is that you only talk about one thing at a time with a state diagram. But it can be a big thing or it can be a small thing. It can be a big thing that has other small things in it, but you just reference one thing at a time. So this is an object. It could be an object, it could be a component, it could be a subsystem, it could be a whole system. So this is the application object, and we can see that at the start, this is called the initial pseudo state. So the first state that it can enter into, and it can only enter into one state when it starts, and that's pending. Everybody sees that? Then if there's an approved event, or an approved event, then it can become approved. If there's a complete event, then it can go into the finalizing state. From pending, if we have a reject event, we can go to a rejected state. If we have a complete event while you're in the rejected state, then we go into finalizing there as well. Yes. No, we're just talking about this system, this object. You know, like when you apply for a bank account, the first thing is that it's pending because it don't get approved because you applied. Somebody has to check it. And then when the person approves it, then it goes from pending to approved. And then afterwards, after it's approved, maybe you need to sign it or put some things on the file, money in that account, and then it will be considered complete or finished. Yes.
So when you say a state diagram, what happens?
Every state machine is describing one system or object or components. It can, that's what I was telling you, it can be an entire system. That entire system may have other things happening in it, you know. But when you're talking about the state diagram, you're saying the state and state transitions of a particular entity. The entity could be a big composite entity, or it could be a tiny entity that's just one entity. But it could just be a tiny entity, you know, with nothing else inside of it. But you only talk about one subject at a time with a state diagram. All right, a state is, of course, the rounded rectangle. That's how we represent it, and we put the name of the state inside of it. We can also talk about what's happening inside of a state. So a state is not necessarily static. So a state doesn't mean that, okay, you're in the state of sitting, and so you just sit. If you're in the sitting state, it's possible that you're writing when you're sitting, or you're reading when you're sitting, or something. So if that's important, and remember, we only reflect, again, we're still talking about abstractions. We talk models are abstractions, so it's still an abstraction. So you only include in the model what is relevant for solving a problem. So if you're talking about something that's happening in the state is important, then you put it in as a do behavior. And to represent a do behavior on a state, in a state model, you use the word do / do copy. Now, different tools will allow you to represent this slightly differently. I'm trying to remember right now what it looks like in StarUML. I think it looks like this. So it might have a symbol beside it as to whether it is an entry activity or an exit activity, which we'll talk about shortly. We're going to talk about it shortly. Now, if you don't need to talk about the behavior, you can leave it out. Then transitions. Transitions have a particular pattern. The first thing that you'll see is the trigger. Sometimes you only see the trigger alone, as in the account application example. You see the trigger followed by something in square brackets, then you're looking at what is the name of the thing in the square brackets? A guard condition. This is not the first time you've seen guard conditions. You saw it in your activity diagrams and you saw it in your sequence diagrams. Everybody remembers that? Okay. So the next thing is our guard condition. And then we have that / again. And when you see that / it's usually telling you about a behavior. So this is a behavior that can happen during a transition. It only happens if the transition takes place. So you have to remember that. Okay? So here's an example. What is this example telling us? I would wait for you to tell me what I'm moving a little fast now, because we're running out of time. So gathering input is one state, processing input is another state. Let's talk about this first transition, this first transition. What does this mean? Keystroke is the
Trigger.
it's the trigger. Keystroke is the trigger. Input less than required length is the guard condition. So what does that mean?
Can I do the behavior?
Right. So it's saying that once somebody clicks a key, then that means it's going to go ahead and do the transition only if, so it doesn't even check the guard condition unless the trigger occurs. So the trigger occurs, then it checks the guard condition if there's one. If there's none, it will just do the transition. So if the input is less than required length, then it will continue to gather input because it goes back to the same state. So what you're summary of what you're saying is true. As long as you have less than a certain amount of input, it will continue to accept keystrokes. That makes sense? Good. It's continuing to gather input. Let's look at this one. What does this one say? So the first thing, it's easier if we just follow it in order. The first thing is that if a keystroke occurs and the input is equal to the required length, so the last keystroke actually causes the input to be equal to the required length, then it will go ahead and submit the inputs. And that's happening during the transition from gathering inputs to processing inputs. So if you didn't have submit input, it would still go into the processing input state. But because the do condition is there, it's saying while you're doing the transition, also do this thing. And that thing is called the doing activity. In this case, it's submit input. Yes, Lauren? Okay, so because this is just a formatting for a transition. So on a transition, it doesn't really say do, but you know that that's a condition for that's the activity that's happening during a transition. Inside of the state itself, you'll see the do. Let's talk quickly about this one. I'll allow you to explain each of them. Let's talk about this one first. Tell me what's happening with this transition here. Somebody online can answer. I feel like I'm missing you guys. Anybody? Press stop or explain that transition. Anybody here? Explain the plain state and the transition to the stop state via the press stop. Okay, so it means that if you're in a plain state, there's something happening during the plain state, and that is reading the disk, right? You know that once you're in the plain state, it means that the disk is being read. It also means that if somebody presses, the transition means that if somebody presses stop, you're gonna change the state from playing to stop. Let's look at this one. No more this. What does that mean?
It can't play.
Do you notice there's no trigger on this one?
If there's no this,
It's automatic. Somebody was saying something online?
I was saying if there's no this, it can't play. So yeah, it's just automatic.
Right. So in the case like no more this, where you don't see a trigger, but there's a condition there, that condition exists. That alone will cause the transition to occur. But, okay, so if you're no more this, then the CD player will change to stopped. Now, if you're in the stopped state, this line here means that from the stop state, you can go back to play. You go back to playing by pressing play, and there must be a disk in the tray. From pause, we can go to stop by pressing stop, then press stop. From pause, we can press play and end up back in playing, and from playing, we can press pause and end up back in paused. And then this one, what does this one mean? Right. So one of the things that you can think about is that this do read this behavior here, when there's no disk to read, when the do behavior stops, it looks to see what next it should do. Now, if it is that nobody has press stop before it's going to a stop state, nobody pressed pause, then the only other conditions, the only other transitions that exist are this one and this one. And they have no triggers. But the condition is what is going to cause them to go ahead. If there was no condition, it would automatically transition. So if there was no condition here, if you ever see a transition line with nothing on it, it means that once the do behavior of the state is finished, it will automatically transition. Understand? So in this case, the only thing that blocks it from transitioning or not transitioning is the existence of additional disk. So whenever there's no disk to read, it will either go into the stop state because there are no more disks. You know those CD players, I know we're not really into CD players anymore, but like people like me, I still remember those CD players that allowed you to start the CDs and then it would play and you could set it so that it could play randomly from the different CDs, or you could set it so that it would play from one CD, finish that CD, move to the next one, play that one, move to the next one, until all, sometimes some of them would allow you to play 5 CDs or 3 CDs. Okay, so you have the ones that you put them there, but I think you have them that you put them in this way as well again. Yeah. So this answered this question already. Do you need to use state diagrams? They are useful for modeling an object that behaves differently dependent on it. So if you want to think about how this is related to the kind of programs that you're writing, you can look back at our account application objects. You can look back at that and you see that this is a normal business type of business or software type of thing. It's not somewhere some hardware thing. It's not an embedded system in some piece of hardware or a car or something, which is where we tend to see the examples, but it can be relevant for business type applications. And you can see that the triggers actually represent the transitions are actually triggered by the calling of certain behaviors upon the object. So if you call the approved behavior on the object, and what it's also telling you is that the approved behavior should not work unless you're in the pending state. So you cannot approve an object from the approved state or the rejected state or the finalizing state. Make sense? Right, and so on. You can apply that concept to the other things as well. So this is a nice one. I love this example. You can look at it for 2 minutes. So look at this one, and you can discuss it among yourselves, and we'll continue next time. Okay, persons online, thank you very much. I have to end here. I'm sorry I didn't, but we have to end here. There's another class going into the room. Bye, guys.
Bye.